Okay, so we are continuing to talk about the rational root theorem. Here's an example. It says use the rational root theorem to help factorize the following. So the fact that it says to use the rational root theorem immediately tells us that if I was to sub in factors of my constant here, so that means if I went p of 1, that's not going to be equal to 0. If I went p of -1, that's not going to be equal to 0. If I went p of 5, that's not going to be equal to 0. If I went p of -5, that's not going to be equal to 0. And the reason why I can say that so confidently is because they've told us to use the rational root theorem. If they hadn't, then I would have had to have tried all of these and figure out that they didn't work. And then once they didn't work, then I would have to start using the rational root theorem, which would have been a real pain. So you should be very thankful to a question that tells you to use the rational root theorem. Because that means what we're going to do now is we're going to say, well, this is alpha, this is beta. What we're going to consider is simply going to be factors of the first one over factors of this one, 1 on 3. So that means the fractions that we're going to consider are plus or minus 1 on 1, plus or minus 1 on 3, plus or minus 5 on 1, plus or minus 5 on 3. So they're all the different combinations that we can make. We can now eliminate those that are integers, like this is an integer and that's an integer because they're over 1. So that means we just need to consider this one and we just need to consider this one. And this is when you start just chucking things in. So we're using our factor theorem here. So if I go p of, and if I went 1/3, you're going to find out that if you did do this, so sub 1/3 into all your x spots, it's not going to work. If you went p of -1/3, you're also going to find out that that does not work. If you were to sub in p of 5 on 3, you would likewise find that does not work. And then lastly, if you were to go p of -5 on 3, you would find that that does work. So this is our one that works here. So this is it, which is very nice. So that's the one that's going to work. So that means that our factor is going to be, now this is where you have to be careful. It's going to be, now let's write this out. It's going to be x is minus 5 on 3. So I would go 3x equals minus 5. And then I would go 3x plus 5 is equal to 0. So that means, whoops, what this means is 3x plus 5 is a factor. 3x plus 5 is a factor. Perfect. Okay, so you can kind of think of this as step 1. Then we go to step 2. Step 2 is divide. So let's come here, and I've got my factor that I just had, 3x plus 5, and I'm going to divide it by my original p of x here. So that's going to be, if I come down here, 3x cubed plus 8x squared plus 2x minus 5. Okay, let's see how we go. Again, we start to freak out a little bit because we have a non-monic, but everything's going to be fine. This is going to be x squared, this is going to be 3x cubed, this is going to be plus 5x squared. We subtract, this is going to be 3x squared, we carry down this 2x, then we start again. This is going to be x, this is going to be 3x squared, this is going to be plus 5x, subtract, this is going to be 3x minus 3x. Then I carry down this minus 5. This is going to become -1 because -1 times that is -3x minus 5. That minus, that's going to be 0. Remember, it's really important that you get a remainder of 0. And the reason why it's important is because we know that 3x plus 5 is a factor, so it should go into that perfectly. Okay, so just a look at what we've done so far. We did the first step, which is a bunch of trial and error. We then divided, and now our third step is going to be factorizing the quadratic. And remember, this isn't always possible, so if possible. So remember, we know that p of x is going to be equal to our divisor, 3x plus 5, multiplied by the quotient, which is going to be x squared plus x minus 1. Okay, whoopsie daisy. So now what I have to do is I have to factorize this. That's what I have to do. I have to factorize this. Now you might begin by going, I need a product of -1, I need a sum of 1, what are those factors going to be? And then you quickly realize after doing this that this is not going to work doing it in this fashion. So instead, what we're going to do is complete the square. You could also use your quadratic formula if you wanted to. The reason why I know, let's take a step back for a second. I know that this isn't going to help me. I can't do it this simply, but I still know that I can factorize it. And the reason why that is because if I was to get my discriminant here, it's going to be 1 minus 4, 1 minus 1, which means it's going to be 1 plus 4, which is going to be 5. So it's a positive number. So that means, there are x-intercepts here. I can factorize it. So that's what my discriminant is telling me, that this can be factorized. So I can use my quadratic, but instead I'm just going to complete the square. So I'm starting with x squared plus x. Now remember, what you're going to do is you're going to plus the coefficient of x, square it, and then subtract it. Then you still have to minus 1 because you still got a minus 1 there. So that means I'm going to get x plus 1/2 squared. This is going to be minus 1 on 4 minus, now this minus 1 I'm going to write as 4 on 4. And then I can go x plus 1/2 squared minus 5 on 4, like that. Now once I've got it like this, I can actually write it a little bit differently. What I can do, just so it looks nice and factorized, is I can write this as x plus 1/2, let me do this up differently, 1/2 plus the square root of 5 on 2. So I'm just square rooting this, close it, x plus 1/2 minus the square root of 5 on 2. So I have factorized this. And now that I've done all that, I can finally say that p of x is going to be equal to, I've still got 3x plus 5 here, 3x plus 5. And then it's going to be this right here, because I factorized this into this. So it's going to be x plus 1/2 plus the square root of 5 on 2, x plus 1/2 minus the square root of 5 on 2. And that's my final answer. So a bit fiddly, yes. There's lots of things going on there, but this is your final answer. So we also had to, take note of that, the fact that, factorizing our quadratic wasn't the easiest thing in the world there, but we did it. Those are the steps to be able to do it. So let's just kind of recap everything that we've done here on this page. So we used our rational root theorem. We first appreciated the fact that there are no integer roots. So then we used our rational root theorem and we found 2 rational roots to sub in. This one worked, and remember that I cheated here. You'd have to do it by hand. You'd have to do it by hand. Let me not write I cheated. And then you divide, then you factorize a quadratic, and then you get your final answer. So a bit fiddly, yes, but that is the rational root theorem in all its glory. Hopefully you found this helpful, and I will see you in the next part.